Let me share my screen. Okay. So, what are we going to talk about today? We want to understand our digestive system. What it does is breaking down your food into molecular components, and we absorb nutrients into our body. So there are a number of, sorry, I'm watching this Kaunashi instead of you, so that my eye can focus on you. Right, so we have a number of organs attached to our intestinal and digestive system. So we do have stomach, pancreas, and liver. And you guys all know what they do: stomach mixing, crushing, and digestion, some digestion. And you have a pancreas, which is wrapping around stomach, and that's a floppy organ. Actually, when you do anatomy with a mouse or rat, you will realize it's hard to find out pancreas because they don't have a solid shape. But the function is very important. It's an endocrine and exocrine secretion. And you have a big liver, relatively, compared to other organs, and that's digestion and regulation of your metabolism. And we'll discuss layered structure of our intestines, small and large intestine, and overall fluid balance. Okay, let's first about, I have to say there's a lot of jargons here, and these are some basic ones. So you will face in your career in medical engineering. I strongly urge you to focus and memorize, at least because this is so basic terms. Okay, so let's get started from the top. So first, GI tract, which is, of course, from anus to mouth to anus, sorry. So oral cavity, pharynx. I put some Korean and Chinese words here so that you guys can understand better. So pharynx, and you have esophagus. It's a pretty long organ, but normally it's collapsed so that when you are burping, you don't get annoyed. It's normally collapsed, but when there's the food, it's of course open. And then it comes down to stomach. Okay, stomach is below your diaphragm. Okay, so it's a pretty long. Okay, and then it gets down to small intestine called duodenum, jejunum, and ileum. So 3 parts for small intestine, and it goes to now enter into your large intestine, which is first beginning at the cecum. Okay, and then it goes, your large intestine. Consider you have a wall watch, okay, onto your belly. Then the way count clockwise is how your colon is rotating. So it's on your right side going up, so which is a ascending colon, and it goes transverse colon, and downwards, which is descending colon, and it goes to the rectum and to the anus and anal canal. Wait, so when you need a better digestion, you use this and not the other way. Okay, you massage your belly like this. So these are number of basic terminology. Hopefully you make sure you get familiarized, because once you know that you have no problem reading New York Times about health issues, blah blah blah. And let's get down to digestive tract a little more. So function, of course, breaking out foods into molecular components, and storage and controlled emptying, mixing, secretion, digestion, and absorption. So let's come into see a little bit different aspects here. So you have mouth, salivary glands underneath your tongue, and parotid gland underneath your ear. So they produce saliva, and you're surprised how much they actually produce a day. And then you have esophagus. And I'll give you some example. Some of you were involved in, let's say, treating animal by giving a drug like every day or every several days. Then you have to use gauge needle. So there are needle which you have to grab the animal, putting that gauze needle into the mouth, but you want to make sure the animal take the drug. And drugs are not yummy, so they will spit out. You don't want that. So you want to put this gauze needle, bring it down to this stomach. Practical tip is you will see that there's a resistance over here and here, because there's normally a valve there, which is closed. So don't push it, because you will make the animal sick and your experiment will be screwed up. What's the trick? You give one drop water, then it'll automatically open. You can put your needle tip inside the stomach, and that's where you actually give your drug. That's how you do experiment for giving the animal drug orally, okay? So after this, so you see there are like valves in here. So valves and SP is a specialized region of smooth muscle to control movement of intestinal content. So let me ask a question to, let's say, Jang Gyo-ho?
Yes, Prof.
Yes, can you guess what this is?
Sphincters.
Great, yes, right. That we call a sphincter, okay? In Korean, hwaryagun, okay? And that you can find out upper esophageal sphincter upward, and at the terminal esophagus, you see lower esophageal sphincter, and also your stomach should have something valve here, so pyloric sphincter over here. And you have a small intestine, which is a duodenum, jejunum, ileum, and that connects to your large intestine. But small intestine content, large intestine contains of bacterial flora, which you never want them to come back to the small intestine. So there exists ileum, like ileum, to secret sphincter. Okay. Of course, you have anus, and that has actually two kinds of sphincter, which is internal and external. In fact, internal sphincter is the voluntary, and external is involuntary. So normally you're fine, but when you're sick, diseased, and sometimes you have an accident because of this, sphincter doesn't work very well. Okay, and the question for you, let's say there will be someone who can answer this. So what about from mouth to anus when you take it out? Actually, I watched this German educational video. They actually take out from the cadaver. What's the length? Can you guess? Let me see. Kim Jong-un?
Yes.
Yeah, can you guess? When you stretch out mouth to anus, how much of the length can you expect?
I don't know where.
I mean, you can guess. You don't have to know the answer exactly.
10 meters.
Oh, very close. Yeah. You know, science is about question and guess, and then testing it out. So you don't have to like memorize numbers, but you get the sense. You're very close. It actually is about 8 meters from mouth to anus, and which is a long, long distance. Like from my room, from the here towards the end, even that's not enough for 8 meters. So here, digestive tract, I put a number of jargons. So hopefully you guys understand parotid gland, meaning that large salivary gland, which is underneath your ear, and upper lower, I already talked. Pyloric, it's a stomach to duodenum. So that different parts, we have a sphincter, ileocecal, and internal and external. And I want to bring a kind of latest research results on this. Hey, we are talking about this macroscopic sphincter, but you know, in our body and circulation, what's the most basic unit for all this oxygen transfer and even nutrient transfer from this digestive tract? Is actually down to the capillary level. So it's a natural for, like, you know, physiologists and neurophysiologists. Hey, at the down, what are controlling our flow for this? And that's microscopic capillary. The question is, do we have a sphincter over there? And the answer is yes. And recently, it's kind of known for a long time, but recently people use it in vivo microscope to actually figure out what's the role, and is there actually sphincter at the controlling capillary, because capillary is the business end of all our transport and exchange of gas at the cellular level. So that's last year in Nature Com, the title, and this guy is an instructor for me in a class that precapillary sphincter maintain perfusion in cerebral cortex. So this is in neuroscience area that what we discover is, hey, there are, like, you remember artery, arterial, and capillary. And even at the junction of capillary, at the first, there's sphincter, which is of course microscopic scale and tiny, but that controls each individual capillary perfusion. So you go to here, you'll see of wonderful studies and how to figure out this. All right, let's go back to our stomach, mixing, crushing, and digestion. And of course, consider about yourself when you are eating a lot, and how much you can eat your food. That's stomach is an expandable vessel, can hold about 1 liter, okay, of food. So of course, mechanically mixing, crushing, chemical digestion to convert solid food into smaller particles. And think about your stomach, where it exists. It's actually pretty low here. This is diaphragm, lower than diaphragm, and it's a junction between small intestines. And this one will have this shape. You see already, this is very muscular, okay? So that's mechanically mixing and muscular contraction and providing mechanical force to helping breaking down the solid food. And at the same time, the stomach secretes gastric fluid. And remember, gastric is the origin of stomach, okay? And gastric fluid is actually giving very acidic liquid. Remember, we all have a experience with the reflux, and that's very, like, painful because it's acidic and almost like hydrogen chloride. So that pH is as low as 1. Why? To protect us from bacteria, because we've got a lot of bacteria coming from the food and from elsewhere. Okay, so what does this pH of 1 means is, remember your normal physiological pH at the body is 7.4. Let's say 7. 7 compared to 1 is 6 digits, which means 1,000,000 times higher concentration of hydrogen ions. Okay, so then your natural question is, hey, that's really harsh condition. How can our stomach not being melt from its own gastric fluid? How can you protect our stomach from low pH? And we have designed to coat our lining of the stomach, which includes this M layer. Let me ask a question for a second. 박지수? Can you guess what this is? 박지원. Sorry, it's not 지수.
Mucus.
Yes, mucus. Right. So mucus layer, which is a heat produced, and then it coats the surface. And of course, so remember all our GI tract, remember these are all epithelial layers, and most of them are coated and maintained with the mucus. Euiheon already showed how to protect ourselves from COVID-19. Mucus is very, very important, okay? And especially in the stomach, there are, you remember from sometimes you've heard enzyme pepsin, and which will initiate protein digestion. So pepsin makes the peptone into amino acid. So you guys kind of maybe heard about this. But you know, this enzyme will digest protein. Then why this enzyme, when it comes out, it doesn't digest the stomach itself? Are you curious? Why stomach produce enzyme and that doesn't eat up our stomach? And there comes this nice design that we produce enzyme, not the original active form, but the precursor form. So that we call pepsinogen. And that pepsinogen is inactive, but until it gets into this condition that a very low pH, it becomes activated enzyme pepsin so that it does its work. So that's a nice design. All right. Now let's get into a pancreas. You guys know pancreas is a very important, but mostly in cancer biology, you know, for over decades, our 5-year survival rate of pancreatic cancer is still like 5 to 7%. It never changed. While the other, like lung cancer, we still have, we are getting very low and low because we know the cause, maybe reducing smoking and environment is very important. But pancreatic cancer, we have no way to treat very well. And it's unfortunate. So not only with that, the function's critical because it's a kind of endo and exocrine organ. So let's look at the pancreas anatomy first. So that pancreas is surrounding or even attached to the your stomach. It's very hard to identify and at first because it's very, very like smooth and it's hard to see. You can see it, but it has an anatomy, and I hope you have all gained the experience of actually touching and seeing the pancreas. It has this shape, and close to this small intestine is called head of pancreas. Of course, the other side, the tail of pancreas. And it connects to the duodenum, and pancreatic juice is coming out through this duct. And pancreas has this digestive enzyme juice, and that we call exocrine, meaning that, you know, it's external. It secretes outside, so it's acts through the duct, and it contains gland. So pancreatic enzymes secreted into our GI tract. But at the same time, pancreas also secretes the special content into our bloodstream. And that part we call endocrine, you know, because it's getting into our circulation, which is pancreatic hormones secreting into the blood. So that cells responsible for this is called islet of Langerhans cell. You remember from diabetes disease, you will hear this term. So endocrine function is secreting this into the blood, and Pradeep, can you guess what pancreas secretes into your blood? Can you guess? We already discussed this before in recombinant DNA technology.
Insulin.
Yes, insulin. Right, that's a very important function of our pancreas. Okay, so without pancreas, it's going to be a problem. An exocrine function digests enzyme into duodenum, you can see over here. And the enzyme in the pancreas, that's, of course, this digestive enzyme, again, similarly, you have digestive enzyme coming from the pancreas, why does this enzyme not digest your pancreas from the beginning? Okay, because they produce this zymogen, that's a protein secret in, yeah, this is a trick. We secrete inactive form, and then it converts into an active enzyme at the site of action, like the environment inside duodenum, it will be activated enzyme. Because of this enzyme, actually the word enzyme is meaning fermentation, okay? Because in fermentation, we use a lot of enzymes, and that is enzyme. Pancreas produce zymogen. This zyme coming from enzyme, and ogen is a precursor, okay? So like we saw stomach and pancreas, this strategy of digestive enzymes in produce it as an inactive form or precursor. And once it gets into the environment, it will start to do their work so that it doesn't digest your own organ. Okay. Now let's get into liver. So liver is a very, very important for digestion, and stored glycogen. So also liver is very important for neutralizing harmful substance. So you remember, like in Korean, like 해독작용, liver, neutralizing. And of course, the liver secretes bile, and which is probably very bitter, okay, for digestion of fat. And those in biomedical engineering, you hear a lot about molecular imaging. That is, hey, you are interested in like cancer or treatment for revealing the size of the tumor growth in your body. And people develop nanoparticles and molecular agents which contains contrast. Then you have to get into the bloodstream so that the molecular probe go to circulation and attach to your, let's say, tumor to reveal. And this, let's say, nanotechnology or in the imaging area, what's the biggest problem? Whenever you inject things into bloodstream, this exogenous, let's say, contrast agent, they get stuck into liver, and the liver will take care of them to reduce them, remove them. So that become a problem, in fact. But that's what liver does, okay? So it's like, let's say, MRI contrast agent, you inject, and then soon the liver updates, so the concentration in the blood goes down in pharmacokinetic point of view. So people are developing molecular agents for molecular imaging, which do not actually absorb, got stuck in liver much, so that they keep in circulation for a longer time for a better molecular imaging. So that's, liver's function, and which is related to our engineering. And I want to get into liver. You know that liver, you can cut the liver part out, okay? If there's a cancer or there's a problem, you can cut, and liver is even a regenerating organ. But the interesting part is such an important organ that has a unit, which is a replicated unit. So that's why you can cut the part. You can't cut the heart, a quarter of heart out, because it's all like having coordinate function, but liver is all parallel. So here comes a unit of liver. Think about this as an engineering point of view. We still do not have artificial liver, okay? To make it, you need to understand in the engineering point how liver has been made. It's a very amazing organ that, look at this. So your liver, so you have a gut. The gut absorbs nutrients from your food, okay? And then that nutrients have to go to liver first, because the liver stores this into glycogen, all right? Even tumor cells from your, let's say, colon cancer, many times they go to the metastasize to liver because of this anatomic structure of hepatic vein. They all get into the liver first, okay? So you look at that, there's a hepatic vein but the name is important, portal vein. Okay, port is the meaning of airport and harbor. Port is meaning of harbor for entering many things, because liver from your intestine, from your stomach, the absorbed one, from your spleen, everything goes to the liver, and this is the venous blood. Okay, and that gets into here, and they are efficiently moving to direct contact with a liver cell called hepatocyte. But at the same time, liver needs oxygenated blood, and that we call hepatic artery. This is directly from your left ventricle of the heart. And they get into, how maybe God designed the liver and how to make this rich in oxygen, rich in nutrients, pour this one into your liver cell. And that's the question. And here's the design mechanism. As I say, hepatic vein, we have a name of portal vein because with all your guts and stomach and spleen, and these highly nutritious venous blood gets in. That's why we pour it as a portal vein. And from the heart, we have an oxygen. We need to shower your liver cell called hepatocytes with oxygen and nutrient. And strangely, you actually send it to the same direction and mix them inside your liver. So this time, and the cell arrangement here, hepatocyte, is very interesting, that it's called sinusoid. What it means is this liver hepatocytes, actually their endothelial cells, they don't make a direct contact. So it's like fenestrated, or it's like a little bit more sparse, so that these and these bloods are mixing well with the liver cells. So that's we call sinusoid structure, a small irregularly shaped vessel, an organ, especially in this liver. So this is very interesting. They actually mix together inside the liver. And so they drain, this is hepatic portal vein, they drain at the center here. So that's why we name it as a central vein, and the blood out as a venous, and it goes to your heart, right outside of the heart. At the same time, the liver produces this waste product, and that waste product can be also changed, converted into content which is good for your digestion, and that's called bile. And the bile duct is on the reverse side, and that's, you see these many tiny duct we call bile canalunculi. So this is a little difficult term, but canalunculus is a small channel duct. So bile canalunculi. Okay, this is a multiple plural form. So here's the design. I want you to understand this is very specially designed organ, and the bile goes to gallbladder and your gut. So all the liver cells perform the same function. That's why you can chop your liver out and still you can live. And it has a unique circular system, which is hepatic artery and hepatic, I said the harbor, portal vein. Interestingly, they both flow into the liver, mixing together. And your liver cell receiving mixture of arterial blood, which contains oxygen, from the heart, okay? And your venous blood from your gut, which is in intestines. Okay, so a course of hepatocytes, which is liver cell, they lie along the pathway from the hepatic artery and vein to the central vein, because the shape is now in this liver unit, they get into the center, becoming a central vein. And bile duct drains in our direction towards bile collecting ducts. Let me see. Okay, so with time, I'll just tell you the answer, reverse direction. So special arrangements for substantial blood flow containing both compounds observed from the intestine. So that's why when you have a toxin or like maybe rotten food, it gets into the liver. And liver contains a lot of immune cells, such as Kupffer cells, liver's macrophage. And they are the one when you are doing your experiment, you inject, let's say, vascular tracers or molecular probe. Unfortunately, the liver Kupffer cells, actually, they take up this as quick as possible. That become a problem for your experiment. And many people who are developing molecular probe are trying to define how to avoid this, okay? So substantial blood containing both observed from intestine, which is of course a nutrient from portal blood through portal vein, and oxygen from hepatic artery, which is arterial blood. They pass a huge surface area of liver cells. That's a special arrangement. And again, the other side is a pathway collection of waste products and bile, which is through this canaliculi structure and gets into the bile. Okay. All right. So so today we discussed about this our digestive system, which the role is breaking down from your solid food from the mouth and to your stomach and through your intestine, its molecular components and absorption of nutrient. And I'm gonna go to the second part. So I'll take less than 10 minutes to explain you the structure, small and large intestine. Let's say about intestinal tube. First, I want to explain you the special arrangement anatomy. So you have this coelomic cavity, which means just body cavity, and your intestinal tube, such as like this tube. In fact, it's not just exist inside your cavity by itself. It actually looks like this. It invaginates, okay? And then that visceral organ. And so you will see this layer is double layer with the serous membrane. That's the key concept you have to understand in this intestines inside your peritoneal space. So this is a little complicated, but I want you to understand this layer structure. We have two layers. First, inside the lumen. Second, you have, when you open up from, when you're experimenting and doing surgery with the animal, first, what you will see out of body work, you will see peritoneum, okay? And then you will have seen this thin layer. You have an intestine, okay? Animal has an intestine. You take it, there's actually a thin layer with a blood vessel. That's called mesentery. And then your the intestines will have inside, there's a mucosal layer. As you see, there's all the epithelial in GI tract is covered in mucosa. And that has a three anatomical structure called first mucous membrane and lamina propria, which is a connective tissue. And inside, it's called muscularis mucosa. Okay, that is connective tissue. You will hear this in your career, I definitely tell you. So try to understand the layer. And then this mucosa below, we call it submucosa. The role is epithelial layer connecting to the muscular layer. And then outer part of this gut and 곱창집, the outer part is called serosa. Right? And also how the food stuff is coming down from the liver is based on this movement. It's very easy. You collapse, constrict the part, so push and release the other part so that it moves down. And here I have to define proximal and distal end. So inside our body towards is called proximal, but in the gut, it goes toward to anus, that's outside. So that direction is called distal. That's how we define our orientation, proximal to distal. And that rhythmic contraction in stomach, 1 minute, only 3 times, very slow. In your small intestine, duodenum, 8 to 10 times of this rhythmic contraction makes pushing your food waste down. And that is called peristalsis. Oh, sorry, the layer is smooth muscle cell, okay? Okay, smooth muscle cell. And then I want to talk about this muscle layer. It actually has 2 layers. So this, you have to constrict, okay? So that requires a circumferential muscle, which is an inner side. Also, you see this peristalsis, you have to move, push it the other longitudinal direction, that is longitudinal muscle. So it's a very interesting design of this, for this peristalsis. So muscular event propelling food through the intestine, you have to coordinate distal relaxation and proximal constriction. Of course, this contains a lot of neuronal network we call second brain. The number of neurons are even maybe equivalent with your brain. So that's why it's very important, the nervous system in your gut. Okay, so absorption in your gut is a small and large intestine. They have a little difference. Small has carbohydrates, protein, and lipids, while your large intestine have a bile acids and water absorption, and it's a little different from small intestine. I want to talk about how food product actually gets into your body, which is eventually going into your bloodstream and moving down to the livers and throughout the body. So glucose as a transporter, it passes through the epithelium. Protein decomposes into amino acid, and amino acid goes through. Sucrose, which is your double like sugar, it decomposes into glucose and fructose, and this single unit, it's getting absorbed. Polypeptide, peptide becoming decomposed into amino acid once it gets in. Triglyceride, it can be decomposed into glycerol and fatty acids and pass through, and somehow they get recombined into triglyceride inside during this digestion. And you see hydrolysis, 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 which when you break it down, you need a water molecule, and then you break down. That's called hydrolysis. And the opposite word of hydrolysis is called condensation. So finally, I want to talk about fluid. You know how much this is just surprising. Hey, we drink water 1 liter a day, okay? The food you are eating contains about 1 liter of water. Your saliva, your spit, you have produced 1.5 liter a day. Your gastric juice inside your stomach secretes juice 2 liter. Your pancreas secretes 1.5 liter. And your bile fluid about 0.5 liter. And also your intestines also secrete fluid about 1 liter. Let's see how much is being absorbed. And your small intestine is an amazing organ to collect 6.5 liter. That's a huge amount reabsorption. And the remaining fluid, your large intestine absorb about almost 2 liter. And when you defecate, your stool contains about 100 milliliter. So you can do this plus and minus, you'll see there is a homeostasis, about 8.5 liter and 8.5 liter. So what you realize is our digestive system secretes large volume of fluid to facilitate digestion, and our intestines reabsorb